Hi there. My name is Alex. I'm one of the tutors for OneClass. So a little bit about me before we begin today. So I got my undergraduate degree in biopharmaceutical sciences at the University of Ottawa, and I got my master's degree from the University of Toronto, also in chemistry. So today I'm going to take a look at some of the most popular questions that pop up on online tests or online assignments that students have chosen. It's going to be a varying range within chemistry, so general chemistry, organic chemistry, but it will focus on questions related to grade 11 chemistry, grade 12 chemistry, and first year university chemistry classes. So I'm going to go through each question step by step, and solve each problem slowly, and draw out the full solutions. Okay, so the first question we're going to start off with today. So the molecule cyanazine, once used as an herbicide, has now been phased out by the EPA because of its significant human toxicity. So the question asks you, so it gives you the structure of cyanazine here. It asks to add lone pairs as needed, and then to indicate the hybridization of the specified atoms that have been numbered here. So I'm going to flip to a PowerPoint so I can draw out the solution for you. Okay. So sorry, one second. My pen ready? Okay. So first we need to add lone pairs to the structure. So what's good to know is carbons have no lone pairs that needed to be added, so we don't have to worry about carbons. Hydrogens just are only able to make one bond, so they have no lone pairs either. So in this case, what we need to look at are all the other atoms that are not carbon or hydrogen. So in this case, we have 1, 2, 3, 4 nitrogens to think about, and 1 chlorine atom. So now nitrogens typically form 3 bonds to be neutral, and as well they have 1 lone pair. So all of the nitrogens in the structure should have an additional lone pair included. Here. This one too, and this one's the last one. Okay, so then the only other atom we need to think about is chlorine. Now chlorine has 7 valence electrons, so we need to account for a few extra lone pairs. So chlorine actually has 2, 3, 4, 3 sets of lone pairs, so 6 electrons in total. If you want to double check to make sure that you have put in the right number of lone pairs, every atom should have 8 electrons, so a complete octet. So in knowing that, remembering that one bond is 2 electrons. So in this case, with this nitrogen, it has 1, 2, 3 bonds, so that's 6 electrons, plus the lone pair, so that gives it 8. A double bond consists of 2 individual bonds, so those should each be counted. So for this nitrogen here, we have 1, 2, 3 bonds, so that's 6 electrons, and then the lone pair, so it gives you a complete octet. So then we have to state the hybridization of the labeled atoms. So the labeled atoms in this case are all the atoms in red. So for state of hybridization, it will either be sp, sp2, and sp3. So in this case, you're only looking at the number of bonds to consider. So for example, this nitrogen atom has 3 bonds, so that makes it sp2. So you subtract 1, if that makes sense. So then this carbon here has 4 bonds, so it is sp3. This nitrogen has 3 bonds, but we're going to count the double bond as one unit. So 1, 2, so that makes this nitrogen sp. Same goes for this carbon, 1, 2, 3, so it's sp2. And this carbon here, yeah, that carbon there is counted for. Yes, this one is, because it has the triple bond that we count as 1, so it's 1 bond there, 1 here, and that is sp. Okay. Oh, sorry. Erase my drawings. Okay. So on to the next question. Okay, so the question asks to select the correct IUPAC name for the following organic substrate, including the R or S designation when appropriate, and draw the major organic products for the SN1 reaction. And it gave you 2 options for the IUPAC name. So we're going to go through this step by step because the question does ask, there are multiple parts of this question to consider. Okay, so first of all we need to give the IUPAC name. So this is the an organization that standardizes the way molecules are named. So there's a lot of different rules to keep track of depending on the different functional groups present in your in the molecule you're trying to name. So in this case, we have to consider mostly carbons in our naming, and 1 hydroxy group is the only functional group that we really need to look at. So what we need to do is find the longest chain, carbon chain, linear carbon chain that can be named. And we want the numbering to include the most number of substituents at the smallest number. So in this case, it may be tempting to start with here as number 1, but then our it wouldn't give us the most substituted, least numbered substituted chain, because if we started here, 1, 2 has no substituents, whereas if we started here, 1, 2, it already has a methyl group to think about. So we're going to start there. So that's 1, 2, this is 3. We could name this methyl group as 4, but we can make it a 5 carbon chain instead of 4, which is preferable. So we're going to keep going up here. So this is 4 and this is 5. So now in our including our naming, we have this methyl group to include this methyl group and the hydroxy group. So we're going to name our chain alphabetically, but we have 2 methyl groups, so we can, instead of saying methyl-methyl, we can just say dimethyl. So we have the 1 on carbon 2, 1 on carbon 3, that is dimethyl. It's a 5 carbon chain, so we have pent, and it is an alcohol. So we're on carbon 3, so it'll be pent 3 all. Okay, so now the last thing we need to do is consider the stereochemistry. So because we have a carbon here that is attached to 4 different groups, that is a chiral center. So it's usually marked by a star, just so you know. So now we need to figure out whether this is R or S. So we need to determine which group is in higher priority. So now normally it is the group with the highest molecular weight. So from this carbon, we go up, that's just a CH2, go down, that's a CH3, that's a CH, and the OH. So the OH is of higher molecular weight because the molecular weight of oxygen is 16, whereas carbon is 14. So this is going to be priority group number 1. Then we're going to look, so this is CH2, CH3, but this carbon has 2 methyl groups on it, so this is heavier. So this is priority group 2. Then in following that, this carbon, the ethyl group here, is number 3, and this methyl group is our lowest priority group, is number 4. So now that we have determined the priorities, we can follow the circle around. So it is going clockwise, which would be R. But our lowest priority group, which is the methyl group, is pointing in the front. So our priority list, it shifts. So the counting goes counterclockwise. So that means that this is S. Had this this group here been dashed or wedged and the methyl group been dashed, it would be R. So you've always got to make sure that the lowest priority group is either in the back or in the front, and that's higher priority. Okay, so now we have named. So now we need to draw the major products from this SN1 reaction. So in this case, it says just to draw the products. It doesn't say to draw the mechanism, but I'm going to draw through the mechanism so that it is, so you understand how the products are formed. But make sure you pay attention to the question, whether it says to just draw products, or it'll specifically say to draw the reaction mechanism to show how you got to the products. So this is an SN1. So that means that it is a stepwise reaction. It's not going to all happen at once. So what needs to happen first, so HBr is our nucleophile, and the alcohol is our electrophile. Now in this case, the alcohol is a poor leaving group. So it won't just leave on its own, but because we are under acidic conditions, we're in HBr, the OH is going to grab a proton from HBr, kick bromine out. We'll end up with this intermediate. The stereochemistry stays the same. Okay. So now we have Br minus kicking around. So this is going to be our nucleophile. It is going to, oh, I'm sorry, I'm drawing SN2. I apologize. I'm skipping a step. Okay, try that again. So what's going to happen is the leaving group will leave first before a nucleophilic attack. That is characteristic of an SN1. So the methyl group is there. Sorry, the methyl group is wedged. Propyl group like that, and then now we have a carbocation because this carbon is only has 3 substituents. So this is not a stable intermediate. So bromine's going to come in right away and form a bond between that carbon. So now I'm just going to draw the product first without any stereochemistry because we need to determine the stereochemistry as well. So it says, the key word here is that it says label the products. So what's going to happen is that we are going to have 2 different products. They're actually going to look exactly the same. But in terms of SN1, you get a mixture of enantiomers in your product. So you're going to have the same stereochemistry retained in one product, and then you're going to have the opposite enantiomer as a second product. So what happens is you end up with 50% of this and 50% of this. It's a completely even mixture. And this happens with SN1. This doesn't happen with SN2. Okay, so now we need to label the products. Now here, because we replaced our first priority group, which was the OH, with the bromine is still the heaviest out of all the other carbon atoms attached to the chiral center. So then this one, is still S. Whereas the other one, because we flipped the stereochemistry, automatically is R. So you can just make that connection without having to go through the priority groups all over again. Okay. So on to the next question. So it's another reaction question, organic chemistry reaction question. This one's a little bit more simpler. So the question asks, draw a structural formula for the major product of the acid-base reaction shown. So here it shows two reactants and then we have to draw the product. A few things to note is that you do not have to consider stereochemistry and you do not have to include counterions in your answer. And in those cases in which there are two reactants, draw only the product from the compound that reacts. Okay, so just flipping back to the PowerPoint. So I can draw out, again, it asks for just the major products, but I'm going to draw out the reaction mechanism so that you understand where the product comes from. So in this case, we have it's an acid-base reaction. So HCl is our acid, and this amide group is our base. Yeah, okay. So an acid is pretty much anything that can donate a hydrogen or a proton, and a base is anything that will accept it. So in this case, the nitrogen atom is the most basic group compared to the oxygen atom. That will be what the electrophile, the nucleophile, it's going to attack HCl. Okay. So what's going to happen is that the NH is going to grab that proton and it's going to kick out chlorine at the same time. So our product ends up being charged. It's not neutral anymore. So it ends up being NH3. And now because nitrogen has 4 bonds, it's positively charged. Now it said in the question, not that you didn't have to draw counterions, but if you did, your counterion would be Cl-. So this forms a salt, which is quite stable. And it will just stay like this. Okay, and that's it. So it also can go, it's usually in equilibrium, so it will bounce between the two, between the salt form and the neutral form. Okay. On to the next question. Okay, so now we are going to name an element in the third period, or the third row, of the periodic table with the following. So we need to name an element with 3 valence electrons, 4 3p electrons, 6 3p electrons, and 2 3s and no 3p electrons. Okay, so flipping over, I have cropped a picture of the periodic table, so it is only showing the first 3 rows, because we only really need to pay attention to the third row. Or the first 4 rows, just to make it look nicer, but this is row 1, 2, 3, 4. So we want to pay attention to the third row here. This one. Okay, so the first one is a name an element that has 3 valence electrons. So in terms of the numbering, it goes, that's 1, that's 2 for valence electrons, so we're going to skip over, that's 3, 4, 5, 6, 7. So these numbers are usually written up at the top of the periodic table. So if we want 3 valence electrons, we'll look at column number 3, or row 3, and we have aluminum. So our element with 3 valence electrons is aluminum. Okay. So then we need to find an element with 4 3p electrons. Over here is P. This is D, and F is the bottom 2 rows of the metals that aren't shown here, so you don't have to worry about those. So now the way it goes, so if we want 4 3p electrons, so that means we're going to have, it'll be start with 1s, 2s, so 2 electrons in the 2s and 1s, so that would be hydrogen and helium in that case. So there's 2, then 2p, which would be this row here, is 2p, and that's 6 electrons. That's the maximum number of electrons in a p orbital. Then we're going to 3s, which is this row here, the sodium magnesium, and that has 2. And we want 3p to have 4 electrons. So if we added it all up, go 2, 4, 6, so that's 10, 11, 12, that's 16. So element with 16 electrons is sulfur. So that is the answer for B. Okay, going through the same method, but we have 6 3p electrons. So that means the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, and it'll be 3p6. So it's full shell. So that gives it 18 electrons. So that makes it argon, as argon has 18 electrons. So then the last one is 2 3s electrons and no 3p. So it stops here. So it'll be 1s, 2, 2s, 2, 2p6, and 3s2, which gives it 12 electrons, and that is magnesium. So the answer for D is magnesium. Okay. It's just, you just kind of need to have an idea as to. Okay. So on to the next question. Oh, sorry. Okay. So here we're going to, the question is to consider this phase diagram for carbon dioxide. So a phase diagram is, so on the y-axis is pressure, usually in atmospheres, and on the x-axis is temperature. So in this case it's written in degrees Celsius, sometimes it's in Kelvin. But what it shows is the temperature and pressure at which a molecule is in all 3 of the phases. So what temperature and pressure it is to be solid, liquid, and gas. And all of these lines show the transition between each state. So the question asks, in what phase is carbon dioxide at 72 atmospheres and 0 degrees Celsius? So if we go to 72 atmospheres, so it's pretty much at the top. On the y-axis, if we go to the x-axis and find 0, which is probably around here, go up to the top. So the phase that CO2 is in at 72 atmospheres and 0 degrees Celsius is liquid. Then the following question, starting from the point described above, so 72 atmospheres and 0 degrees Celsius, so up in here, what phase change would eventually result from a decrease in pressure? So if we went decreasing pressure from 72 atmospheres, but still at 0 degrees Celsius, if we were to make it fall down, it would go from a liquid to a gas. So the phase change described here would be condensation. Oh, sorry, vaporization. I'm so sorry. Vaporization is from liquid to a gas. Condensation is from a gas to a liquid. Deposition is not a phase change. That's just thrown in there to mess you up. Sublimation is gas to a solid, so this transition state here. Freezing is from a liquid to a solid, so from liquid to the solid, crossing over here, so at much lower temperatures. Like I said, vaporization is from a liquid to a gas, and melting is from a solid to a liquid. So it's just good to know the names of all those phase changes. Okay, on to the next question. Okay, so what kind of intermolecular forces occur between toluene and hexanes? Okay, so I'm going to flip back to my PowerPoint just so I can draw out what toluene and what hexanes looks like. So that should help give you an idea as to being able to identify the molecular forces between the two. So toluene is an aromatic ring, or a phenyl ring, like that, but it has one methyl group. So this is toluene. Hexanes is a linear alkyl chain made of 6 carbons. So 2, 3, 4, 5, 6. So this is hexane. So there are 3 intermolecular forces to consider. The strongest one being hydrogen bonding. Second being dipole forces. Third being London forces. This is also sometimes called van der Waals forces. They're the same thing, just different names. So looking at these two, H bonding would be HO bond, HN bond, or HF bond. So these are the only 3 atoms bound to a hydrogen that can be considered a hydrogen bonding intermolecular force. So now between toluene and hexanes, there are no oxygens, no nitrogens, no fluorines, so only carbons and hydrogens. So there are no hydrogen bonding intermolecular forces. Now dipole forces, here there are no atoms other than carbon or hydrogen. So there are no dipole forces, leaving only London forces between the two. So they're just very small interactions between the two molecules, very easy to break. Okay, that was a little bit of a shorter question. Good concept checking questions though. Okay. The next question, what state best describes an O3 molecule? So they give you 3 selections. So A, an ozone molecule contains 1 single bond and 1 double bond. B, the double bond in ozone switches back and forth between the 2 outer oxygen atoms. And C, each atom in ozone is connected to another atom by a bond having a bond order of 1.5. Okay. So what needs to be seen, you need to know what ozone looks like to be able to answer all of these questions. So here at the bottom, I will draw out ozone. So ozone is O3. So we have 3 oxygen atoms linked together. Okay, so oxygen prefers to have 2 bonds. It can have 3 and it can have 1, but 2 is ideal. But in this case, the most accurate structure of ozone is to draw a double bond here. So now this oxygen atom is happy. This one has 3 bonds, so that's going to make it positively charged. And this one only has 1 bond, so that makes it negatively charged. But because you have 1 positive charge and 1 negative charge, it's neutral. The charges cancel each other out, so it's fine like that. So then, looking back at the question, so an A is an ozone molecule, contains 1 single bond and 1 double bond. So this is a correct statement. We have 1 single bond, 1 double bond. As well, because our structure is relatively symmetrical, that double bond can move around and distribute itself. So it can move to this oxygen-oxygen bond. So this oxygen is still positively charged because no matter where that double bond is, it still has 3 bonds. But now this oxygen is negatively charged. So what happens is that the molecule bounces back and forth between these 2 structures. So then looking at B, the double bond in ozone switches back and forth between the 2 outer oxygen atoms. So that is also correct. So now what needs to be considered, so this is our resonance structure, I'm just going to break it off like that. But if we were to combine these 2 resonance structures into one, this is how you would draw it. So no matter which resonance structure, there's at least 1 bond between the central oxygen atom and the 2 outer oxygen atoms. But that double bond flips back and forth. So the best way to show it is through a dotted line that goes all the way around. So this shows that the double bond could be at either side at any time. So because of this, the ozone has 3 bonds at one time, but because that extra bond is moved back and forth, this gives our ozone a bond order of 1.5. And looking at statement C, each atom in ozone is connected to another atom by having a bond having a bond order of 1.5. So it's 1.5 here, 1.5 here. So that makes this statement correct as well. So then the answer for this question would be all of the above, because all 3 statements are true. Okay. So moving on to our 8th question. Okay. So it's a little bit more of an involved question. So we have to provide the missing compounds and reagents shown in the reaction scheme below. So to make this easier, I just copied and pasted the image onto the PowerPoint so I could draw on it. Okay. So we're going to follow this in order. So this is where we start, and then this is where we end. So here, what needs to be done? This question has drop-down menus, so it will have a selection of different reagents that you can choose from. Because this is just a screenshot of the question, I cannot select any. I can't see the drop-down menu, so I'll just have to give the answer. But that'll usually make it easier for narrowing it down if you know what reagents do what. So here we have the cyclohexane ring remains the same. So the only thing that has changed from reactant to product is that we went from a hydroxy group to a ketone. So to go from a hydroxy group to a ketone, this is known as an oxidation reaction. So I'll write that up here. So the most common reagent to do this transformation is PCC, which is probably included in the drop-down menu. Then from the ketone, we have added a methyl group and reduced our ketone to an alcohol. So to do that, you would need to do a Grignard reaction. So first would be the Grignard. So we added the methyl group, so that's part of the Grignard. So we have CH3. And a Grignard reagent is anything that is attached to magnesium bromide. So that adds the methyl group. As well, typically in a Grignard reaction, you need acid. So we can just write it as H3O+, just to reprotonate your alcohol to make it stable. So now, so this time they gave us the reagents for the reaction, but we have to draw the product. So now, if you need a little bit of help, you can try to look ahead to see what's changed. So one thing that hasn't changed is the methyl group. So the CH3 is still there one step later. So that probably means that we kept it throughout. But we have the OH group has moved carbons. So that means that we had to get rid of the OH group first and then add the OH group later. So POCl3 is like a dehydrating reagent. So what it will do is it will get rid of that proton. We'll do this and kick that out, because it will make the OH group into a chlorine, so that makes it a better leaving group. And pyridine is a base. It looks like this. So that would have been the reagent that deprotonated the hydrogen alpha to the methyl group, allowing the double bond to be installed. So now we have broken this double bond and added a hydroxy group. So there's one way to do that is through using BH3 borane. So that'll add a hydrogen group to the methyl group and then a BH2 group here instead of replacing the alkene. But because there's no BH2 group, in the final product, that means we quenched it. And you would quench it with hydrogen peroxide. So that will swap out the BH2 for an OH group. So now from here, we are going from a alcohol, a hydroxy group, to a ketone. So we already did that in the first step. So most likely we used PCC again to do that. So now we have to kind of look ahead a little bit. So because we have to find the reagent and draw the product in this case. So in this situation, it's good to count the number of carbons in the final product versus where you are. So this is 1, 2, 3, 4, 5, 6, 7, 8. This has 6, this is 7 carbons. So that means we added another carbon somewhere. So now I know that POCl3 does the same reaction as above here. So that didn't add a carbon. That just got rid of the OH group and a hydrogen. O3 ozone does not add a carbon. It is an oxidizing reagent, so it would just add to an OH. So that must mean that we use another Grignard to add another carbon. So we'll probably add just another methyl group because it's just one carbon. So using methyl magnesium bromide. Don't forget that we also need acid to quench. Okay. So then our product will look like this is still a CH3. Then we quenched and ended up with OH, and then we added another methyl group. So that gets added. So now POCl3 will do the same as above, but it will take this hydrogen to form the double bond again. So this is CH3, CH3. We lost our OH group, turned it into a double bond. So ozone cleaves double bond and turns it into two hydroxy groups. So that opens up the cyclohexane ring, and we end up with this linear diketone product. So a lot of these take a lot of practice, but once you feel really comfortable with different chemical transformations, doing these kind of full synthesis questions really helps to make sure you fully understand all the chemical reactions you've learned. Okay. On to the next question. Okay, so the question is, consider the following mechanism. Which species is an intermediate and which species is the catalyst? So now because it's sideways, that makes it a little difficult to read, so I fixed it on my PowerPoint. Okay, so we need to find the intermediate and we need to find the catalyst. So by definition, an intermediate appears in the product of one step, the reactant of another step, and does not appear in the final overall reaction mechanism. So here in step 1 we formed ABC, so as a product. That product is used as a reactant in the second step, but ABC together does not show up in the final product. So that makes it our intermediate. So this is intermediate. Just change color really quickly to make it a little bit easier to see. Okay, so then our catalyst. A catalyst was something that will appear at the beginning of a reaction and will reappear at the end, but has not changed. It's stayed completely the same. But it will not appear in the overall reaction. It will get canceled out. So in this case, when you want to see the overall reaction, you're just adding up the reactants with the products. But if you see a species that appears on the left-hand side of step 2 and the right-hand side of step 1, they cancel each other out, so they do not end up in the overall reaction. So our intermediate gets canceled out. We'll eliminate that. And then what also gets canceled out here is A. So A is not an intermediate because A by itself does not show up in the reactants of step 2, but A shows up in step 1 and in step 2, but not in the overall reaction. So that means that A is our catalyst. So our intermediate is ABC, and A is our catalyst. And the rest are just reactants. So here it's 2BC because you have a BC from step 1 and BC from step 2. So those two just get added together. And then the remaining products are B2 plus C2. Okay. On to the next question. Okay. So the question is, draw the structures of the intermediate compound, so that would be after step 1, and the final organic product in the following two-step reaction. And the molecular formula of the product is given. So I have written it out. I will do it step by step. Okay, so I'm going to draw out the mechanism, but the question only asks you to draw the intermediate and the final product. So you don't have to draw out the mechanism for this. So here, our nucleophile in this case is the alkene, and our electrophile is Br2. Now note that it says that it happens in the dark, so this means that it is not a radical-based reaction. You can do the same reaction with Br2 and an alkene in the light, but the mechanism is different, but you still end up with the same product. So in this case, it doesn't really matter because it didn't ask you to draw the mechanism. So what's going to happen is that the alkene is going to attack the bromide. Bromine is also going to attack the other carbon of the alkene, and that bromine is going to leave. So this is an intermediate of step 1, but not the intermediate that the question is asking. So what's going to happen is that we've formed a bromine carbon bond between both carbons of the alkene. So we form this brominium intermediate, which doesn't last very long because we have minus Br kicking around that's going to pop this open. And then we're going to end up with our intermediate, so our product of step 1. Which is a dibrominated product. But there's no bromine in the chemical formula they gave us. So we're obviously not there yet. So this is intermediate after step 1, or the product of step 1. Then step 2, we have KOH, which is a base. Ethanol is the solvent, so ethanol, it looks like this. So we have a proton here and a proton here that are fairly basic, or fairly acidic, sorry. That could be deprotonated. So KOH is ready to grab a hydrogen because once it does, it forms H2O. It forms water. So that's very favorable. And bromines are very good leaving groups. So we're going to grab the proton, reform a double bond, and kick out bromine in the process. So this is the intermediate of step 2. So we formed an alkene here, but we still have a bromine here. And because we have a lot of KOH kicking around, we're going to do the same thing twice. Form the alkene, kick out the brother. That's terrible. Okay, that's still there, and we have another aromatic ring now because we added the additional 2 double bonds. So if you count up the carbons and hydrogens in the product, so we have 10 carbons and 8 hydrogens. So we have 1 H all around the ring here. Okay. So, and that matches, so that is the correct answer. Okay. So, on to the next question. Okay, so we are going to classify each compound as ionic or molecular. So we have CO2, carbon dioxide, nickel chloride, sodium iodide, and PCl3. That's an L, not a 1. Okay, so flipping back to the PowerPoint. Okay, so a molecule is defined as 2 nonmetals bound together. And an ionic compound is 1 metal bound to 1 nonmetal. So the periodic table is grouped based on metals and nonmetals. So you can take a look at that. So that'll help you determine each element, if it's metal or non-metal, so then that will tell you if a compound is molecular or ionic. So CO2, so both carbon and oxygen are metals, or non-metals, I'm sorry. So that means that it is a molecular compound. So it means that we have formed bonds, covalent bonds in between the elements. It makes it molecular. Nickel chloride, so nickel is a metal, but chlorine is a non-metal. So this is an ionic bond. So this means that they're not attached to each other by a physical bond, but they are attracted to each other by an ionic bond. Nickel is positively charged, chlorine is negatively charged. So C, so we have sodium iodide. So sodium is a metal, but iodide is a nonmetal, so this one is also ionic. So this is the ionic bond. Oops, sorry, that's supposed to be sodium. iodide is negatively charged. And PCl5, as phosphorus and chlorine are nonmetals, this would be molecular. The way it would look is like this. We were to draw out the structure. With 5 chlorines. So quite a lot going on. Okay. Okay. On to our next question. Okay, so we're going to write the chemical equation when sulfuric acid reacts with sodium hydrogen carbonate. Okay, so first we need to know the chemical formula for sulfuric acid and the chemical formula for sodium hydrogen carbonate. So sulfuric acid is H2SO4. Sodium hydrogen carbonate is NaHCO3. When we react them together, we form sodium sulfate, which is Na2SO4, plus CO2 gets released, the carbonate part does, and then we also lose water as byproducts. So now, to balance this out, I'm going to keep, there's a lot of elements in this chemical equation that need to be kept track of. So I'm going to make a little chart. So we have hydrogen, sulfur, oxygen, sodium, and carbon. So the number of each in the reactant side and the number on the product side. Draw that further down. Okay. So hydrogen, we have 3 on the reactant side, 2 on the product side. Sulfur, there is 1 on the reactant side and 1 on the product side, so that's good. Oxygen has 7 on the reactant side and 7 on the product side. Sodium has 1 on the reactant side, but 2 on the product side. We have 1 carbon on reactants and 1 carbon on product. So now the rule of thumb is to balance all atoms first, except for oxygen, hydrogen, and sulfur. Oxygen, carbon, and hydrogen, sorry. So we can balance out sodium and sulfur. Sulfur we don't need to balance out. It's already pretty good to go. But we have 1 less sodium on the reactant side. So we're going to draw a 2 here. But now that changes how many hydrogen atoms, carbon atoms, and oxygen atoms we have. So now we have 2 here. But now we also have 2 carbons. We have, 4 hydrogens. And we have, how many oxygens? 4, 6, 10. So now we've balanced our sulfur and our sodium. Now we need to tackle carbon, oxygen, hydrogen. So first we are going to balance the oxygen atoms. So here we have 10 on the reactant side and 7 on the product side. So what we need to do to balance that out, so we will put a 2 on CO2. So now on the product side we have 2 carbons, so that's good. But now we have 4, 5, 6, 8. We have 9 oxygens on the product side. So we're getting there. We balanced the carbons, which is good. But now we need to add another oxygen atom. So to do that, we'll just put it 2. So that'll give us an added oxygen atom, so that's 10. And then it also ends up giving us 4 hydrogens. So those are all balanced and already ready to go. So you just want to double check your numbers, make sure we have 2 sodiums, 1 sulfur, 1 sulfur, 2 carbons, 2 carbons, 4 hydrogens, 4 hydrogens, 4, 6, so 10 oxygens, 4, 8, 9, 10 oxygens. So now the equation is balanced. So it's always good to double check on those kinds of questions, because sometimes you lose some numbers while you're doing all that math. Okay. So for the question, it says be sure to answer all parts. Draw a stepwise mechanism for the following reaction. So in this question, we have benzyl bromide on the reactant side, and then we end up with a benzylic ether. Okay. For this ether group, so in this case, this is ethanol, so we can also write it like this. This is our nucleophile, and our bromine is our electrophile. It's a good leaving group. So now that we've determined it's a substitution reaction, we need to know if it's an SN1 or an SN2. The best way to determine that is based on the carbon attached to the leaving group, if it is primary, secondary, or tertiary. So here it's attached to two things. So this is a secondary carbon, which means that if it was to go through an SN1 mechanism, it would not be able to hold the carbocation intermediate, because you need more substituents to kind of stabilize that positive charge. So this is going to be an SN2 reaction mechanism. So the first step is nucleophilic attack onto that carbon. And then simultaneously, because this is SN2, you're going to kick out the bromine. Okay. So our intermediate looks like this. So we still have the hydrogen attached, and that makes the oxygen gives it a positive charge because it has 3 bonds. But we also kicked out Br-, which is going to grab that hydrogen, going to kick the electrons back to the oxygen, and that's going to give us our product. So for completion's sake, you can also write out that you formed HBr as a side product. Okay, so it's pretty straightforward. It's just hard, as long as you can identify what kind of reaction you're doing, the mechanism shouldn't be too difficult to figure out. Okay, so the next question is, how do you count sigma and pi bonds? So a chemical bond is the attractive force that exists between atoms, ions, and molecules, due to which different chemical compounds are formed. Pi bonds are formed by side-to-side overlapping of atomic orbitals. So a sigma bond is like this, whereas the pi bonds are on top of each other like this, floating. So to figure out the number of pi bonds versus sigma bonds, you need to determine the number of single bonds, double bonds, and triple bonds. So, and you'll need to remember that a single bond contains 1 sigma bond, a double bond contains 1 sigma and 1 pi bond, and a triple bond has 1 sigma bond and 2 pi bonds. So that's what is shown in this little table here. So that's just something you're going to need to remember. And then once you have remembered how many sigma and pi bonds are in each type of bond, if you had a full molecular structure and they asked you how many sigma bonds In pi bonds, you would just have to count keep track of all the different types of bonds, and remember that double bonds have a sigma and a pi bond, and triple bonds are a sigma and 2 pi bonds. Okay. So the next question is order each of the sets of compounds with respect to SN2 reactivity. So number 1 being the fastest and 3 being the slowest. So flip back to the PowerPoint. So this goes back to the previous question where we determined if it was SN1 or SN2. So SN2, the faster reactivity happens when it is primary. Not really. It's super slow. It would go through an SN1 mechanism faster than it would go through an SN2. So in this case, we're going to look at the carbon which is attached to the leaving group. So this one is primary. This one is secondary. And this one is tertiary. So in knowing that a primary carbon attached to a leaving group is the fastest, this one is ranked number 1. This one is 2. And this one's tertiary, so this one is 3. So now in terms of leaving group capabilities, I'll do it over here. Iodide is faster at leaving than a bromine, which is way faster than a chlorine. So in knowing that, the SN2 reaction of this iodo compound would be number 1, bromine being 2, and this one, even though the structure is not the same, the leaving group is what you really need to pay attention to. So this one is 3. Okay. So now we're going to switch. We've done a lot of organic chemistry questions. So now we're going to do some math and do some general chemistry questions. So the question says that iron is mined from the earth as iron ore. Common ores include F2O3, F3O4, and FeCO3. So the question asks to calculate the mass percent composition of iron in all 3 ores, and which ore has the highest iron content. So basically we're going to do the same calculation 3 times. So I'll go through the first one slowly, make sure you're following along, and then I'll go through the other 2 a little bit quicker because the calculation is exactly the same. So if we are looking at Fe2O3 is our first one. So whenever a question asks for you to calculate the mass percentage, you can safely assume, and this will make your calculations much easier, that you're starting with 100 grams. So we're starting with 100 grams of Fe2O3. So now, as a tip for any sort of math-based chemistry question, even if you're stuck, it is a good idea to convert to moles. So usually you have to do that anyway, so it's a good idea just to convert to moles, and then you can try to figure out the question a little bit easier from there. So in this case, to go from grams to moles, we need the molecular weight of Fe2O3. So the way I'm going to do this is it's called dimensional analysis. So instead of doing the math step by step, I'm going to write out all the calculations as one row, and then do all the multiplying and dividing at the end. And the reason I do this is that it allows me to keep track of my units, so that way all the units will cancel out to give you the unit you want in the end. And then this way you don't have to keep track of whether do I divide this number, do I multiply this number. As long as your units cancel out, you did it the right way. So to convert from grams to moles, I'll need the molecular weight of Fe2O3. So the molecular weight is 159.7 grams per mole. So I inverted it so that my grams will cancel out. My grams of Fe2O3 moles will give me moles of Fe2O3. Okay. So now we can, the question asks for the mass percentage of iron, not the mass percentage of the molecule as a whole. So in Fe2O3, for every 1 mole of iron, there's 2 moles of iron, because it's Fe2. For every 2 moles of iron, after that, we need to convert it back into grams because we need to know, we want the mass percentage. So we need to calculate the number of grams of iron from Fe2O3. So the molecular weight of iron is 55.85 grams per mole. Iron. Okay. And that, if we do the full calculation, so we can cancel out all our units now. So we have grams of Fe2O3, cancels out with grams. Moles of Fe2O3 will cancel out here. Moles of iron, cancel out with moles of iron. And we end up with 69.8 grams of iron. So now the last step is just to be able to get it into a percentage. So we're going to divide by 100, multiply by 100%, because remember we started with 100 grams. So the answer in grams actually is also the answer for percentage, so 69.8%. Okay, so we're going to do the exact same calculations for Fe3O4. So 100 grams to start. The molecular weight of Fe3O4, periodic table. So this would be the mass of iron times 3 plus the mass of oxygen times 4, which gives you 231.5 grams. Now we need to convert that into moles of iron. So here we have 3 moles of iron. Over 1 mole of Fe3O4, Multiply that by the molecular weight of iron, which we know is 55.85 moles of Fe. And this gives you 72.4 grams of iron, which divide by 100, multiply by 100%, gives you 72.4%. CO3, do the exact same thing again. So the molecular weight of FeCO3 is 115.85 grams. And now we only have 1 iron atom in the molecule, so it's just 1 mole of iron over 1 mole of FeCO3. You could skip this step if that was intuitive to you, but if not, I like to write it all out just to so that I can cancel out all my units at the end. Okay, we're going to multiply that by the molecular weight of iron again. And that is going to give us 48.2 grams of iron. Divide that again by 100 times by 100%. Gives you 48.2% of iron. Oops. Okay. So once you've got the calculation done once, it's much easier to do it another few times. Okay. On to the next question. So it's sideways again, but so it's draw aspartic acid at pH 1, pH 7, and pH 13. Include hydrogen atoms. So it already gave you the structure of aspartic acid at pH 1. So at pH 1, that's acidic pH. So that means, so the groups that you need to pay attention to is this OH here, this OH here, and this NH. So at pH 1, it's very acidic. So that means that everything is going to be protonated. So this is normally an NH2 at neutral pH, but in acidic pH it is also protonated, so it actually has a positive charge because nitrogen has 4 bonds. Yeah, so everything is fully protonated, making it's not neutral. So pH 7 is neutral pH, because don't forget the scale goes from 1 to 14, so 7 is being in the middle. So I'm just going to draw a quick arrow like this. So at pH equals 7, I'm just going to draw out the structure. So at neutral pH, we end up with the neutral molecule. So we lose, so this is NH2 instead of NH3. So there's no charge. But it is neutral, so that proton on the OH stays there, just the same, as well as the proton on that OH. So now we have pH 14. So this is a very basic pH. So our NH2 is going to stay the same because it's not very correct for nitrogen to have a negative charge. It can happen rarely, but it's usually either neutral or has a positive charge. So our regular carbons, our carbons aren't affected by this. You can't deprotonate a carbon atom with the acid base. So it's very basic, so that means that OH is going to turn into O-. CH2 stays the same, and this also gets deprotonated. So it'll have an overall charge of -2. Okay. Okay. Next question. Okay. So it asks to calculate the bond energy per mole for breaking all the bonds in methane, which is CH4. So the question gives you a list of the bond-to-bond energy in kilojoules per mole. So these are measured values. These never change. So to break a carbon-carbon bond, it would cost you 347 kilojoules per mole. Carbon-carbon double bond is 611. Carbon-hydrogen bond 414. Carbon-oxygen bond, single bond, 360. Carbon doubly bonded to an oxygen, 799. Single bond between two oxygen atoms, 142. Two oxygen atoms double bonded to each other, so O2, is 498, and an OH is 464. So the higher the bond-to-bond energy, the more energy it takes to break those bonds. So we have all these numbers given to us, but we only care about the bond energy for breaking all the bonds in methane. So all you're doing is breaking 4 CH bonds. So the only number you care about is this one. So to break a CH bond is 414 kilojoules per mole. And you're breaking 4 of them. So it's just 4 times 414 ends up giving you plus, because it can also be negative, plus 1,656 kilojoules per mole. So in the options it gave you, D is the correct answer. Okay. So the next question Write the balanced neutralization reaction between H2SO4 and KOH in aqueous solution. Phases are optional. And then after you've done that, so you have 0.55 liters of 0.43 molar H2SO4 mixed with 0.5 liters of 0.26 molar KOH. What concentration of sulfuric acid remains after neutralization? So it's a little bit more heavy on the math for this question. So we'll take it one part at a time. So we need to write a balanced neutralization equation. So starting with H2SO4. It said phases were optional, but I'm going to write out them anyway. So that's aqueous plus KOH, just solid. Okay. And that's going to give you K2SO4 aqueous plus H2O, which is liquid. So now we need to balance the chemical equation. So just looking at it quickly, we have one sulfur. We have two KOH on potassiums on the product side, so we needed 2 here. But now we have 4, 5, 6 oxygens. We have 5 oxygens here, so we're going to add a 2 here, so that gives us 6. Just need to check the hydrogens to 4 on the reactant side and 4 on the product side. So this is now fully balanced. So now we can figure out the concentration of sulfuric acid that remains after neutralization. So like I said earlier, if you're stuck, the best way to start is to calculate moles. So what we're going to do is we're going to calculate the moles of sulfuric acid and the moles of KOH. So now instead of giving us the mass of each, it gave us the liters of each and the molarity of each solution. So sorry, this is aqueous because it's in solution. Okay. So all we have to do, so if we're going to start with H2SO4, it gave us 0.55 liters. So we're going to multiply that by the molarity, so it's 0.430. So capital M, molarity, is short for moles per liter. So what that gives us is 0.237 moles of H2SO4. Yep, okay. So then doing the same here, just squiggle. So we have 0.5 liters of KOH. We have 0.260 moles per liter solution of KOH. So that is going to give us 0.130 moles of KOH. Okay. So now we need to figure out how much sulfuric acid is left in moles after it's reacted with KOH. So as you can see here, we have more moles of sulfuric acid than we do of KOH. So that means we've started with more sulfuric acid than we needed to have react with KOH. So there will be some left over. So to calculate how much we have left over, we're going to add the moles of both. So 0.237 moles of H2SO4 plus, minus, I'm sorry, we're going to subtract the moles. 0.130 moles of KOH. We're going to divide that by 2. Okay. So that gives us 0.172 moles of H2SO4 left over. Yeah, so we divided by 2 because we have 2 of KOH to account for. Okay, so we figured out how many moles are left over. We just need to convert that into our concentration. So we need to turn it into molarity, the moles per liter. So how we're going to do that is that we have 0.172 moles. We're going to add the amount of liquid we added in the pot together. Because in the question it said that we added 0.55 liters of sulfuric acid and 0.5 liters of KOH to get the total molarity of the solution. So then we have 0.1633 molar H2SO4 left over. Okay. Good. So flipping back to some more organic chemistry. That's enough math for a little bit. Okay, so it says draw the major organic product for the same substrate with two different conditions. So I drew out the same substrate twice, just so that I could draw out the answer a little bit more clear, but under two different sets of reaction conditions. So the differences here are in the reactants. So here we have sodium ethoxide. So this is a strong base, but it is also a small base. So the way this looks is Na plus OET, so O ethanol, ethoxide, strong base, so it's also a small base. In terms of steric hindrance, which you'll know what I mean in a second. Here we have potassium tert-butoxide. So what this looks like is K plus, O minus, and has a tert-butyl group. So it has 3 CH3s coming out of it. So now this is also a strong base, but it's a hindered base. This is a very bulky group, so it will change the reactivity. So here we have under basic conditions, so it's not a substitution reaction. It's going to be an elimination reaction. So we have chlorine, that is our good leaving group, so we're going to kick out the chlorine to form an alkene. So now here the question is, which proton do you deprotonate? So you can deprotonate this one. You can deprotonate this one here, but that gives you the same product because the structure is symmetrical, so it doesn't matter. Or you can deprotonate from the methyl group. So we'll just write it CH2. You could deprotonate here. Now this being a small base, it can very easily access this proton. So what it's going to do, if I draw out the mechanism, it's going to take that proton, we're going to form an alkene, and we're going to kick out the chlorine. So it forms the alkene there, the methyl group remains the same, and our byproducts, just to know for completion's sake, is sodium chloride and ethanol, which also just looks like this, which is our protonated base that is now neutral. Now, when it comes to our strong base but hindered, it wants to take this proton, but it can't fit. That chlorine blocks its way. It's too big. So it is going to take the most easily accessible carbon or proton, which is off of the methyl group. So what this does, if I draw the mechanism again, it's very similar to it's the same as the one above, sorry. Kick out the chlorine. You end up with an external alkene. But you've also formed potassium chloride in this case because the base is different, and you formed tert-butanol, like that. Okay, so you really need to pay attention to the characteristics of your reagents to make sure you draw out the right product. Okay. Next question. Okay. So which of the following statements about peptide bonds are true? So the first statement, peptide bonds are ester linkages. B, peptides are polymers of amino acids. C, peptide bond formation is a hydrolysis reaction. D, a tripeptide contains 3 amino acid residues. E, peptide bonds form from nucleophilic attack by a carboxyl carbon atom on an electron pair of an amino nitrogen atom of another amino acid. Flipping to the PowerPoint, because it'll be easier if I draw out an example of a peptide as well as the reaction between 2 amino acids. So an amino acid, the backbone structure, consists of an amine, a carboxylic acid, and I'm going to write R as a generic group, but this is what differentiates between amino acids. So this is what this R group is, can be determines what kind of amino acid it is. So it is, like, if it was a methyl group, then it would be alanine. If it was isopropyl group, it would be valine, methionine, on and on and on. So those are things that you would have to memorize. There's no trick to know what all the different kinds of amino acids are in their structures. But for the point of this question, sorry, I drew that wrong. Okay, going back. Forgot the carbon, sorry, go that way. There we go. Okay. Another R group, doesn't matter. It could be the same amino acid, it could be different, the reaction's still the same. So what happens is this nitrogen atom is going to attack the carbonyl. So the nitrogen is our nucleophile, the carbonyl is an electrophile. I'm not going to draw out the full structure mechanism. I'm going to draw the shortcut that you shouldn't draw on an exam or a test. So the electrons from the carbonyl go up, but they also come back down in 2 separate steps, not just one, and kicks out the hydroxy group. So the product that is formed, our group stays the same. So now we have formed an amide bond. Okay. So here I'll write R2 and this is R1, just so you can differentiate between the 2 amino acids. So you can see that they are 2 amino acids linked by this CO carbonyl NH, this amide bond. Okay, and water is released as a byproduct when you do that. Okay, so going back to the question, which statements are true? Peptides bonds are ester linkages? Well, no, because we just formed an amide bond. If it was an ester linkage, this NH would be an oxygen. So this is not true. Peptides are polymers of amino acids. So what I drew here, I reacted one amino acid with another to form, this is a dipeptide because it has 2 amino acids, 1, 2. If it had 3 amino acids linked together, it would be a tripeptide, on and on and on. So now every peptide has a free carboxylic acid group that can be reacted with another amine of an amino acid, and the chain can just keep going and going and going forever. So then the statement peptides are polymers of amino acids, that is true. Peptide bonds are, peptide bond formation is a hydrolysis reaction. So a hydrolysis reaction is the addition of water, whereas we released water as a byproduct. So this reaction is actually called a dehydration reaction because we sucked water out of it, we removed it, dehydrated it. So then this is incorrect. D, a tripeptide contains 3 amino acid residues. That is correct because a dipeptide has 2. If we added on another amino acid, it would be a tripeptide. So it would have 3 R groups in that case. And then the final one, peptide bonds form from nucleophilic attack by a carboxyl carbon atom on an electron pair of an amino nitrogen atom. So what it is saying is that this carbonyl carbon would attack the nitrogen, which is not true. That is the complete opposite of what would happen. So the nitrogen is the nucleophile and the carbonyl is the electrophile. The carbonyl could never attack anything, it just gets attacked. So this is incorrect. Okay. Moving on to the next question. Okay. So the question is, which compound is likely to have an incomplete octet? So to answer this question, you need to draw out the Lewis structures of all 4 compounds. So CH4, so carbon is our central atom. We have 4 hydrogens around it. We don't have to consider lone pairs in this case. So if we count the number of electrons that carbon has, we have 4 bonds, 2 electrons in each bond, so that gives us 8. So this has an octet, a complete octet. So it's not this one. PF5, phosphorus is our central atom. And we have 5 fluorines dancing around it. Fluorines all have 3 lone pairs, 3 sets of lone pairs to draw in. Okay, so then all the fluorines have a complete octet because they have 8 electrons each. The phosphorus has 5 bonds, 2 electrons each, so it has 10 electrons. So it does not have an incomplete octet because it has too many electrons, not enough, instead of enough. So it breaks the octet rule. So this is called an expanded octet. So it's one of the exceptions to the octet rule. And it is stable like this. No charge is needed. It's totally neutral like that. So then NO2 is like this. We have lone pairs on the oxygen atoms and a lone pair on the nitrogen. Or you can draw its resonance structure, depending on, sorry, there's a negative charge here. Depending on which way you want to look at it. Both are correct. So the negative charge is on that oxygen instead. I'm drawing our lone pairs. But in this case, so our nitrogen atom has 1, 2, 3 bonds in a lone pair in both situations, so in both resonance structures. So it has a complete octet. The double bonded oxygen has 2 bonds, so that's 4 electrons there, 2 lone pairs, so that's 8. But this oxygen, because it has a negative charge, has lost an electron from the lone pair, so it only has 7. So oxygen only has 7 electrons, so this is the structure as a whole that has an incomplete octet. So we just need to check the last one, which is silicon, O2, SiO2. I'm going to draw in my lone pairs. So silicon has 2, 4, 6, 8 electrons. Each oxygen has 4 electrons from bonds, 4 from lone pairs, so it has 8 electrons for every atom in the compound. So it is a complete octet. Okay. On to our next question. Okay, we're going to do a little bit more math in this one. So the question is, determine the pH of a 0.461 molar solution. And it gives you the Ka, which is 6.510 to the negative 5. Okay. So if I were to draw out the dissociation equation, so we have C6H5 CO2, throw in the C there, CO2, H. And if it were under basic conditions, so if it got deprotonated, it would look like this, minus plus H plus. Okay, so we need to write out the acid-base equilibrium equation. So Ka is going to equal, and it's balanced. We should always double check to make sure our equations are balanced, no matter what, but it is. So Ka is going to the products over the reactants. So it's going to be C6H5CO2 minus H plus all over C6H5CO2H. So now it gave us Ka, 6.5 times 10 to the negative 5. And we're going to assume that the concentration of each is X, because we don't know what that is yet. So X for each one. And then we know that we started with a 0.461 molar solution of the starting reactant. So that means we're going to have X less of that if this reaction were to take place. Because you're not going to gain more, you're going to lose some. Okay, so we're going to simplify the equation a little bit more. So this becomes X squared. Now in this case, we are assuming X is a small number. So you can make that assumption in this case. So we're going to assume that it is 0.461. We're eliminating the X because it's so small it won't even change the number. So taking this, and we're just going to solve for X, we're going to end up with 0.004547. Okay, and the question said determine the pH. So our pH is going to be the negative log of our acid, so H plus. So because X is 0.00547, that means that it is the concentration of H after the reaction is done. So the negative log of 0.00547 equals, our pH is 2.26. Okay. So on to the next question. We are going to write the ion product expression for silver carbonate. Okay, so we kind of just did the same thing with Ka. Oh, sorry. Okay. So here instead of Ka, we're going to think about in terms of KSP. So silver carbonate is Ag silver carbonate O3. So this is solid. But if you were to dissolve it in water, you would end up with this ion equation. So Ag plus, sorry, that's aqueous because it's an ion, plus our carbonate, CO3, 2 minus. This is aqueous. Oh, sorry, I wrote the 2 right away, but I was just balancing the equation. So it's better to write like this because it's a complete ion. It's not going to be separated into carbon and oxygen individually. Okay, so we have 2 silvers and 1 CO3 on each side. So it is balanced. So we're just writing on the ion expression. It didn't ask us to calculate anything. So KSP equals its products over reactants, but in terms of an ion product expression, you're only looking at ions. You're not including this solid starting material. So we care about the concentration of silver, which has a coefficient of 2, so that means it's going to be squared. The concentration of CO3, 2 minus, which has a coefficient of 1, so you don't need to draw an exponent. And that is the ion product expression. Okay. Well, on to the next question. Okay. So specify the reagent you would use in each step of the following synthesis. So I just took a screenshot of that so we could look at it. Okay. So here we have an aldehyde, and 2 steps happened, and we ended up with a ketone. So the first thing that happened is most likely the addition of this phenyl group. So we probably formed this bond first. So in doing that, if we're looking at our reagents, so this A is a reducing reagent, lithium aluminum hydride. So what that does is it would reduce a ketone or an aldehyde to an alcohol. So as we go from aldehyde to ketone, that doesn't happen because it wouldn't account for the addition of the phenyl group. This is an acid, another acid, acid. This converts OH to Cl, which we have no chlorines in here. This converts OH to Br. We have no bromines. DMP is an oxidizing reagent, so it would convert OH to either ketone or an aldehyde, depending on what it was attached to. So I'll just write it as O. This is a very strong base. This is another base. This is a Grignard, so this would be used for the addition of a methyl group, which we don't have here. We have the addition of a phenyl group. So this is another Grignard. So anything attached to methyl magnesium bromide, or magnesium bromide, sorry, is Grignard. But this would add an ethyl group. This one is another Grignard, which would add a phenyl group. So C6H5 is a phenyl group. This one is also a Grignard, which would add an isopropyl group. And this is also an oxidizing reagent. But it would go from, like, say, alcohol to a carboxylic acid. It's a very strong oxidizing agent. So in this case, we decided that the first step was the addition of a phenyl group. So we're going to use phenyl magnesium bromide first. So that would give us this intermediate. Okay. So usually after you do a Grignard, you need to add acid to reprotonate to form your alcohol. So you could use H2SO4, HCl, HBr, yeah, from this list. Any acid would do. So now step 2, we have to convert the alcohol to the ketone. So it's an oxidizing reaction. So here, sorry, I'm going to write that out. So we have phenyl magnesium bromide as step 1 for step 2. So we need an oxidant. So like I said, we would either use DMP or chromium trioxide, but DMP is specific to converting a secondary alcohol, such as this one, into a ketone. So it would be DMP, would be your oxidant in this case. But if you wanted to go from ketone to alcohol, you would use lithium aluminum hydride to go back. But once you have formed a carbon-carbon bond, you can't go back. It'd be too difficult to do. Okay. And winding down, probably have time for a couple more questions before the end. Maybe just one more. Yeah, just one more. This will be our last question. This one will take a little bit longer to do. So the question is to construct the molecular orbital diagram for H2+, then identify the bond order. Make sure you add electrons to the boxes corresponding to MO is molecular orbital for the molecule, and to the boxes corresponding to the AOs, so the atomic orbitals, which are here, for the atomic species. Okay. So I'm going to draw it out. So we're going to deal with the atomic orbitals first, and then, okay, there we go. Okay. To start, you want to show that you're going from lowest energy point to higher energy. So you just need to include that y-axis. So H2+ is 2 hydrogen atoms coming together to form a molecule. So we need to take into consideration one hydrogen is forming H2+, and then the other hydrogen. So hydrogen only has one electron in a 1s orbital. So you've got one electron is one arrow. If it had 2 electrons, the arrow would be pointing the opposite direction. They can't point in the same direction. So same for the other hydrogen atom. So these are the atomic orbitals for hydrogen. So now we want to know what happens if you combine 2 hydrogens together to form H2+. So you're going to form our sigma bonds because it's going to be a single bond between each hydrogen. So we need to account for one, this is a sigma bond. So this is our bonding orbital, but there's also an anti-bonding orbital. So this is sigma star. So if we were to draw out the electrons for H2 without the plus, neutral hydrogen gas, we would have 2 electrons because it's 1 + 1, 2. So it would be 1 electron here and then another electron here. You fill in order. If we had 3 electrons, the 3rd electron would go into the anti-bonding orbital. And your electrons are always pointing in the opposite directions. But in this case, we have H2+. So plus means we lose an electron. So this is what our molecular orbital diagram would look like for H2+. Now just as a side note, even though this wasn't part of the question, but just so you can know the difference. So if we had to draw the molecular orbital diagram, for H2-, we'll get there. Okay, if we had to draw it for H2-, our orbitals would still be the same because we're still dealing with the same atoms coming together. The minus or plus charge just impacts the number of electrons. So if we had H2, neutral, it would be 2 electrons in the 1 sigma orbital. But because we have H2 minus, the negative charge adds an electron. So we're going to add an electron into the sigma star. Yeah, so when you draw these out, it's easiest to draw them for the neutral species. And then just remember that if you have a positive charge, you are losing an electron. And if you have a negative charge, you are gaining an electron. Okay. And that is all the time that we have for today. I would like to thank you for watching the stream, and I will be following the similar format, answering the most popular chemistry questions that students have, and I will do that as another live stream on next Wednesday from 4 to 6. But if you happen to miss the stream, this video will be recorded and then will be posted online for you to access as well. So thank you so much, and have a good night.